Okay, we are recording, hopefully. Okay, how is everybody doing? Doing okay? All right. I wanted to first talk about assignment number 3 and go over that with you guys to make sure it's clear. So if there are any misunderstanding, we can take care of it. If you have any question, please ask. Assignment number 3, which we talked about sets. The question number 1 was the collection. First, determine which collections are not well defined and therefore not set. Number 1 says the collection of all the part-time and full-time students currently enrolled at Southern California Seminary. Here we have a very clearly defined universal set, all the students at Southern California Seminary. And then also the members of the set are well defined, part-time and full-time student. Therefore, this is a set. Now, question number 2 says collection of the elderly full-time student currently enrolled at Southern California Seminary. Now here, in this question, the element which is not well defined is the element of elderly. What do you mean by that? You got to be specific. What age group are we talking about? Therefore, this is not set. So this is one of them. Or question number 3, the collection of even natural numbers greater than 100. Turn off my cell phone so we will not have interruptions. And this can be set also because even natural numbers are well defined and there's a boundary greater than 100 going to infinity. So among these 3, only number 2 is not a set because the term elderly is not well defined. Okay? Now let's go to question number 4. It says express each set using the roster method. Okay. Yeah, what age? What age do you consider elderly? Over 50, over 60? Some people can argue with you on that. 60, 65. It's not well defined. Okay. Now, question number 4, it says the set of months of the year that have exactly 30 years, we want to define them in a roster form. Therefore, we need these braces. So the only months that are exactly 30 days are April, June, September, and November. So you write them just like that. Okay? This one, it says a set where X, of a set for all X such that, remember the bar means such that X is a lowercase letter of the alphabet that follows D and comes before J. Now notice it says follows D, so it cannot include D. And it comes before J, so it cannot include J either. So the only one would be E, F, G, H, I. I cannot go to J. All right? The set of natural numbers less than or equal to 6. Again, the roster form N for the natural number equal to, we put these braces, less than or equal to 6. So I must include 6 because it says equal to 6. 1, 2, 3, 4, 5, and 6. Number 7, the set of even natural number less than 10. No, it says only less than 10, not equal. So I cannot include 10. The even number would be 2, 4, 6, 8. I must stop. Question number 8, all X, where X belongs to natural number and X is less than or equal to 4. So here we have 2 conditions. X must be a natural number and less than or equal to 4. So it will include 1, 2, 3, and 4. because that symbol here, less than or equal, means you must include 4 also. Okay, now, these 2 questions, lots of you guys had problem. Let me, it says, first of all, it says, given this universal set, U, A, B, C, D, E, and set A has 2 members, B and C, and B has B, C, E, find each of the following set. A union of A and B not. You see, first you have to find the union of A and B, and then not. I will show you, I will show you on my pad how it works, but just by looking at it, a union means it has to be in both of them, both A and B. What is in both A and B? B and C, okay? Then it says prime it, make it not. So you write B and C and then not. So you go to the union set, not B and C means it includes A, D, and actually, because B, C, and E are all there. So it would be only A and D. But let me show you with the pad, which makes it easier.
So that not.
Yeah. Yeah. You got to be careful about those things. Let me, for example, go to another share a screen to show you how it works. Okay. All right. So we have a universal set. Then we have a set A, and then we have a set B. Okay. I think the universal set was, if I remember correctly, A, B, C, D, and E. Then set A was, let me just make sure that I'm reading it correctly. Set A was B and C, and B was B, C, and E. So set A is B and C, and B is B, C, and E, okay? So we want to find a union of A and B, but then you got to prime it, not. What is in both A and B? You have A, B, we have, well, let's see, either A or B. A, B, C, and E. This is the union, okay? This part. A, B, C, and E, okay? Now, what is not, then you go to the universal set, U, and cross this thing. So you don't want A, you don't want B, you don't want C. Actually, the union, I'm sorry, it can include E, because it has to be in both of them. So you get the union would be A union B. You get wait a minute. B, C, and E. I'm sorry, I made a mistake myself here. Let me clean this. B, C, and E, that's a union. Forget what I wrote here. Okay. So you have, this is the union, but then not, so you cross B, C, and you need to have A, sorry. So when you prime it, when you put prime A union B prime, you get rid of B, C, and E, so you only have A and D. Okay? You follow me? Brian, are you following me?
Yes. Mm-hmm.
All right. Sorry about this. Let's go to another one. The next question was, let me again, let's go to the shared. Okay, the next question was we want to have here we want intersection, not A and B. So you find not A and B, then make the whole thing not prime. Okay, so this is a little bit tricky. So let's go to our other share screen. All right, again, let's define what we mean by, so we have a union set, you have a set A, we have a set B, okay? Our universal set is A, B, C, D, and E. Our set A was B and C. And set B was BC. Okay. And we want not A intersection with B, but then make the whole thing not. Okay. First, let's find what is not A. Whatever in the universal set which is not in A. A has B and C. So not A would include A, D, and E. Okay, following me? Now, intersect that with B. What is common with not A and B? Well, A is not, D is not, E. The only thing that is in both of them is E. Okay? Are you following me?
Mm-hmm.
No, well, I want to find intersection between A naught and B. The only thing that is common in both A naught and B is the element E. Follow me? So, intersection of A naught and B is element E. But that's not the answer. I don't want that. I want A naught intersection with B naught, with B, then make the whole thing not. Following me? So I go to the universal set. I say the intersection of A naught and B is E, yes? So whatever is not E, so I cross E, I get A, B, C, D. So it's, sorry, A, B, C, and D, and we put the braces, okay? Are you following, Brian?
Barely.
Okay, here, let's go over it again. This is our universal set.
Right.
Okay, this is set A, this is set B. First, we find, we want to find, forget this one for now. At this time, don't even think of that. We want intersection of not A and B, okay? So I need to find what is not A. Not A, whatever in the universal set, which is not in A.
I got that part.
Okay, A is B, C, so not A would be A, D, and E. Now, I find not A. I want to intersect that with B. What is common between both of these sets? This one and this one. The only common element is E. Yes?
Mm-hmm.
You follow me? So the intersection of A naught and B is set, has only one element, E. Following me?
Yes.
Okay. Now, the question asks, prime this, make it not. Not A, B, not. Are you following?
Yes.
Okay, so I go to, I say, this is my not A and B set, E. To make it not, you go to the universal set, cross E, whatever is left is the answer, A, B, C, and D. So you see, the key is this. Go step by step. Go from inside to the outside. Start from the inner part going outside. First we find what is A prime. Then we find what is A prime intersection with B. Then when we find the answer, which was E, we prime that. We made what is E naught. And that was answer.
So we use the second step.
Yeah, you know, each step you go forward, you are having a new set. First, we started with A naught. First of all, I just want to find what is this. I don't look at the rest of the question. A naught is A, D, and E. All right. Then I want to find intersection of A naught with B. Intersection of A naught and B is E. So don't forget about the rest of them. Now only think of here. Okay? Now make that prime. Make it make this set, whatever you call it, let's call it for easy to use, let's call that F. If I want to find set F, now make that F to F prime or F naught. So you say set F has only E. So to make it not, you go to the universal set, cross E, and you get A, B, C, and D. Okay, are you following me, Brian?
Yeah, I think where I lost you the first time was when we went back to A naught and the intersection of B and make the whole thing not. I went back to the one just above it instead of going back to the universal set.
Okay, no.
That's where I lost you.
Yeah. The universal set remains. The universal set means you only have these elements.
Right.
There's nothing else.
Okay.
Okay? So let's again go to the next question. All right, then I think these other questions we don't need to go to iPad. Then it gives us, given these symbols, write each Egyptian numeral as Hindu Arabic. You guys did all of this correctly, so everybody got these right. And also these one right. The only thing that some of you had problem was this last one, number 14, which was actually the easiest. Look, it says, if these symbols correspond to this Mayan numeration corresponds to these numbers in our number system, then what would be this number? In fact, this is not correct. I mean, I have to change that. This is not correct. Actually, the answer is 50 because you have 5. The bar is 5. This oval-shaped thing look like a baseball. It's 0, so the answer is 50.
So between.
Yeah.
I screwed the
No,
numbers.
no, no. It's just that these numbers are like that. So it would be 50. Okay? Or Brian, are you following me?
Yes.
Okay. All right. Then let's go back to our PowerPoint. No more, any question from that assignment? Okay. So, all right. Let me go here. Stop. PowerPoint. Okay. Now we want to talk about number theory, the real number system. Let me make this bigger. Number theory is a branch of mathematics that we study different types and forms of numbers. We use number for counting and all kind of numbers. Counting numbers that we use in everyday life are also called natural numbers. And they begin with 1 and continue to infinity. So if you want to put them in a raster set form, would be n is equal to, again, you put these ellipses, then 1, 2, 3, 4, 5, and then you have these 3 dots, braces, and then 3 dots. Okay? This is called a set of natural number. Now, any natural number can be expressed as a product of 2 or more natural number. For example, 2 times 3, 6, 2 times 5, 10, continues. 2 times 4, or 16 is 4 times 4, or whatever. Now, numbers like 1, 2, 3, 6, 9, and 18, they're all factors of 18. What we mean by factor, it means that 18 can be divided by itself or any of these numbers in a way that remainder is 0. When we talk about divisibility, we say if A and B are natural numbers, we say that A is a divisor of B, or A is divisible by B, or A divides B, and we symbolize it by this. A, the horizontal bar, B. If the quotient of B divided by A has a remainder of 0. If we say A divides B, then B is divisible by A, we write it other way around, B bar A. Okay? For example, we say 4 divides 12. It's symbolized by 4, a bar, and a 12. Because the quotient of 12 divided by 4, when you divide 12 by 4, the remainder is 0, and the quotient is 3. Okay, so we say 4 divides 12, or we can write it as 4 divides 12. Okay, these are just symbols. Okay, every factor of natural number is also divisor of that natural number. Now, don't confuse A divides B and these things, A, B, or A divided by A bar B means A divides B. A, when you have the slanted B, means A divided by B, or A, the sign of division. Don't confuse them, okay? All right? Everybody is okay? Brian, are you okay?
Yes.
Okay. Now, we come to prime. Here's the important thing. Prime and composite numbers. Every natural number greater than 1 can be classified either as prime number or composite number. A prime number is a natural number greater than 1 that has only exactly two factors or two divisors, either itself or one. A composite number is a natural number that is divided by a number other than itself and one. The number one is neither prime or composite. It's called a unit. If I show you an example, you will know what I mean. For example, here are you have the numbers from, one is a unit, so we don't put it there, from 2 to 100. We want to find what are the prime numbers between 2 to 100. All the prime numbers less than 100. So we cross out 1 because that's not a prime number, that's a unit. Circle 2, and then that's a first prime number because 2 can be divided only by itself and 1 without no remainder. Then cross out all the multiples of 2, 4, 6, 8, all the way to 100. Then do the same with 3. Then do the same with 5. Do the same with 7, and until you come to 11. So when you do that, you get here. We cross 1, we circle 2, because 2 is a prime number. 2 can be divided only by itself or 1, and the result, the remainder is 0. So we multiply, we cross all the multiples of 2. 4, 6, 8, 10, 20, 28, everything like that, all right? Then we do the same with 3. 3 is a prime number because it can be only divided by itself, 3 by 3, 1, no remainder, or by 1. And so I circle 3 and then I cross out all the multiples of 3, like 6, like 9, like 12, like 15, like 18, like here, 33, okay, all the way to 100. And I do the same with 5, with 7, 11, 13, and keep going. The last one is 97. So all the numbers that I have circled, these are all the prime numbers, less than 100. They are natural numbers, and they can only be divided by itself or by 1 and have no remainder. Okay? And this was a method that a Greek mathematician in 3rd century BC created. Okay? Any question? No? Shall I continue?
Mm-hmm. Yep, proceed.
Okay. Now, this gives us, these are important when you want to find factors. Composite numbers are numbers that can be divided other than itself and 1. Every composite number can be expressed as a unique product of prime numbers. Now we use factor tree to find prime factorization or composite number. To find prime factorization of a number, you select 2 numbers whose product is the number to be factored. And you keep going until you get all the factors that are prime. Let me show you an example to make sense. We get the number 210, okay? This method is called factor tree, okay? So 210 can be the product of 2 times 105. Agree? Now, 2 is a prime. There's nothing I can do, so leave it there. But 105 is a product of the 3 times 35. 3 is a prime, so leave it there, but 35 is a composite. This is a composite number. 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 Now, 35 is a product of the 2 prime, 5 and 7. When I get to the level that the products are all prime, you stop there. So if I want to say what are the prime factorization of number 210 is 2 times 3 times 5 times 7. You get 210. Or you can look at 210 as a multiple of 14 and 15. 14 is a multiple of 2 and 7, and 15 as 3 and 5. These are all prime. Same here, 2, 3, 5, and 7. 2, 3, 5, and 7. You multiply them, you get 210. Okay? Shall I continue?
Yes.
All right. Now, you may want, there's another method. You can find prime factorization by division. So you have, for example, this number, 34,200. You divide it by 2, the first prime number. You get this. You divide this number by 2, and then continue. You divide this number, can be divided by 3. You continue all the way till you come here. 19 is a prime, so you stop. So this 34,200 is a prime factor of 2 times 2 times 2 times 3 times 3 times 5 times 5 times 19. Multiply them, you get this number. All right? Everybody is with me?
Mm-hmm.
Okay.
Yes.
Okay. Now, we have two important things in math. One is called great common divisor, and then another one is the least common denominator. Now, when we want to find the greatest common divisor, or GCD, the GCD of a set of natural number is the largest natural number that divides without remainder every number in that set. For example, what is a GCD of 12 and 18? What is the greatest common divisor? What is a number that is the largest number that both these 12 and 18 can be divided by it? Well, you find the prime factors. 12 can be divided by 1, can be divided by 2, 3, 4, 6, and 12. 18 can be divided by 1, 2, 3, 6, 9, and 18. When you divide them, there is no remainder. Now, you look at, we want the common divisor and the greatest common divisor. So I look at these, the common divisor are 1, 2, and 3, and 6. But the greatest common divisor between these two sets, which one is the greatest? 6. So there is no number larger than 6 that both 12 and 18 can be divided by and have no remainder. Agree?
Mm-hmm.
Okay. For example, when we find the GCD of 2 or more numbers, you find a prime factorization. List each common prime factor with the smallest exponent. Pay attention to here, smallest exponent that appears in each of the prime factorization. Then find out the product as a factors found in step 2. Let's look at an example. Examples. Exponent, remember, like 2 to the power of 3. The 3 would be exponent. Okay, let's look at, for example, page 232. I hope you, if you look at page 232, and just for the sake that, if you don't have the textbook, let me go to our pad and make this, clean up this. Okay. We have example 3, we have number 216. Finding the greatest common divisor for 216 and number 234. Okay. Now 216, we use the 3 factoring, can be 2 times 108. Okay. Now 2 is a prime, so I leave it alone. We come to 108. 108 can be factored as 2 times 54. Are you following me? Yeah.
Yes.
Now 2 is this. I leave 2 alone. I come to 54. 54 is the factor of 2 and 27. Now 27 is not a prime. I can still factor it. It's a product of 3 and 9. And 9 is not a prime. I can still continue. 9 is 3 times 3. Now, all the result that I have here are prime. Okay, so I stop. These are all prime. So I can say 216 is equal to, how many 2's do I have? 3 of them. So I write 2 to power of 3. This is the exponent. Okay. Times how many 3's do I have? 1, 2, and 3. Okay. So I can write it like this. Now I come to this number, 234. It can be the product of 2 and 117. Okay, 117 can be the product of 3 and 39. 39 can be written as 3 and 13. Okay, now these are all prime, so I stop there. So 234 can be written as 2 to power of what? 1, because I only have 1 2. Okay? 3 to power of what?
2.
2. 13 to power of what?
1.
1. So I write it like that. So now you want to find the GCD. I'm sorry? Yeah, you can put it 1 or not put it, doesn't matter. Now we want to find the GCD, the greatest common divisor. We say in order to do that, you look at what it's in both of them and use the least, the number with a you use the one with the least exponent. So I have 2 here, I have 2 here. Which one has the smallest exponent? This one. 1. Following me? Okay, so I just 2 to power of 1, or you don't have to write it. I have 3 here and I have 3 here. Which one has the less exponent? 2.
34.
Shall I put 13? No, because it's not in both of them. We want greatest common divisor. So this is it. So it actually, the answer would be 18. 2 times 3 times 3 is equal to 18. So the where?
Is it saying greatest common?
It is common. You see, let's look at it this way. Divisor means it has to divide both of them. Common, it has to be work for both of them. And the greatest. So we want a greatest divisor, but the one that is common for both of them. And the one that you only find when you do the factorization is when we put the prime factors that are in both numbers, we get the 18. See, it has the word C here, common, divisor, and the greatest. Greatest common divisor. You cannot go, in other words, it means you cannot go to a number more than 18 that divides both of them, and you get no reminder.
Because what I was confused with is that they were playing today,
Ah.
and they wanted instead of 2 to the power of 3, it's 2 to the power of 1.
Because if I pick the 2 power of 3, that is not common in the other one.
Oh,
That C limits me. That C, the common, sets the boundary. Now, let's look at an example that you have here in the textbook. Let me clean up here. Example 4. In the textbook says, we have a league that you need to divide 40 men and 24 women into all male and all female teams so that each team has the same number of people. In other words, what is the largest number of people that you can be placed on each team? So we have 40 men and 24 women. Okay, we want to divide them into teams of all male and all females. We want to know that has all of that have these teams have the exact same number of people. We want to know what's the largest number of people that we can place in each team. In other words, you want to find the greatest common divisor. Okay, so 40 men, 24 women. I do the prime factory or prime tree. 40 can be 10 times 4. 10 can be 5 and 2, and 4 can be 2 and 2. So the factor tree for 40 would be 5 to power of 1, you don't need to write it, times 2 to power of 3. Okay, I come here, 24. 24 can be 2 times 12, and 12 can be 2 times 6, and 6 can be 3 times 2. So 24 would be 3 to power of 1 times 2 to power of 3. Okay, so what would be the GCD? The common, okay, remember the common divisor, but the greatest. That means how far can I go up, but it's still the number must divide both 40 and 24. Well, 5 is not common, 3 is not common, it's only 2, which is the same in both cases, 2 to power of 3, which is equal to 8. In other words, if you want to have a team, when you have 40 men and 24 women, you want to have teams of all male or all female, and you want each team have this exactly the same number of people. In each team, you need to have not more than 8 people. Actually, exactly 8 people. Because then you can have 5 male team and 3 female team. Okay? Following me? Good, good. Okay. Now let's go back to our share the screen. You know something? I just remember something I wanted to mention. I feel it bugging my mind. Actually, this was correct. You know, let me. I don't know how to erase this without maybe. You know, remember the question that we talked about a Mayan numeral system? This is 5, this is 0, but the positions of 5 because of their position, this is set in a set 1 position. We get 100. This is 5, but this is, no. Why am I talking about? No, I'm sorry. Forget what I said. It's 50, what I said in the beginning. There's something back of my mind. All right, let's forget that. All right, let's go back. Are you guys doing okay?
Mm-hmm.
Okay. How are you guys feeling about this course so far?
It's challenging,
Yeah.
different type of thinking.
Okay. But both of you are doing fine, and everybody else, you guys are doing fine. I am giving more than what you will need to know for the tests and quizzes. So, and you see, math comes by practice. You cannot follow just by reading these words. You just have to do the practice, as we just did in these cases, okay? So but try to grasp every level when we go forward. If there's something that you don't understand, make sure to ask. Okay. Okay, we talked about these. Okay, let's move on. Let me just make sure that I'm in a right place. Okay. Now, another thing that is very important is the least common multiple, LCM. The least common multiple of a set of natural number is the smallest natural number that is divisible without remainder by each element of the set. Now, what is the least common multiple of 12 and 18? You see, just by reading this, you get some understanding, but it won't help you. You got to do the practice. What are the multiples of 12? 12, 24, 36, and go on to 144. What are the multiples of 18? 18, 36, 54, 72, and go on. I want to find the least common multiple. The least common multiple of 12 and 18 are 36, 72, 108, and 144. The least common multiple of 36 is the smallest number that is, and then these are some of the multiples. The least of them is 36. In other words, is the smallest number that is divisible by both 12 and 18. 36 is divisible by 12, quotient 3. 36 is divisible by 18, quotient 2, and no remainder. Okay? Now, I'm not expecting you to memorize this thing right now. You will learn it by doing it. How to find the LCM of 2 or more numbers? Again, do the prime factorization for each number. List each prime factor now with the greatest exponent instead of the least exponent. And then find out the product. Let's do one of them to see what we are talking about. So let's go to page 234 and 235 of our textbook. Let me go there. In our pad. Okay. If we go to page 234, example 5, so we are page 234, example 5. Says find the least common multiple of 144 and 300. So if we do the prime factorization, 144 is 2 times power of 4 times 3 to power of 2. 300 is 2 to power of 2 times 3 times 5 to power of 2. I'm not going to do the 3. You can do it yourself, and then you come to these answers. So we want to find LCM. So it must be common, and it must have the one raised to the greatest power. So what do we have common? We have the only exponent that occurs on 5 is 2, so we select 5 to power of 2. When we select every prime factor that occurs raised to the greatest power to which it occurs in this factorization. So what you have, actually, you are looking at all the factors, all the prime numbers to the greatest exponent. We have 2, we have 3, and you have 5, okay? It doesn't matter if it's not 5 is not there. We want all the primes in both of them, and we want them to the greatest power. So it should be 2 to power of 4, 3 to power of 2, and 5 to power of 2.
So, question.
Yes.
So it's just a principle. 5 is not there.
Yeah, I included for LCM. For LCM only. Least common multiple, because it's a multiple. But you choose the greatest exponent. Okay. So the number, and if you multiply these two by together, you get this number, you get 3,600. 3,600, so the least common multiple of 144 and 300 is 3,600. It means when you find multiples of 144 and multiples of 300, the number which is common between both of them, if I write the multiples of both of them, the number that is common in the multiples of both of them, and it's the least, would be this. Okay? Let's look at, for example, another example. Example number 6. This is an interesting example. It says a movie theater runs its films continuously. One movie runs for 8 minutes, and a second movie runs for 120 minutes. Okay, there's a movie theater. One movie goes for 8 minutes, another 120 minutes. Both movies start at 4 p.m. Okay. When will the movies begin at the same time again? When would at 4 p.m. they start? We want to know at what time again they both start at the same time. Okay. This one, when it says it is 8 minutes, it means it's 1 hour and 20 minutes. This means it is 3 hours, okay? 80, if we want to find its prime factorization, it is 2 to power of 4 times 5. 120, the prime factorization is 2 to power of 3 times 3 times 5. All right? The least common multiple, LCM, should have 2 times 3 times 5. 2 to power of 4, I choose the greatest. 3 to power of 1, 5 to power of 1. And if you multiply these together, you get 240 or 4 hours. 240 minutes or 4 hours. So the next time, if they start at 4 p.m. at the same time, the next time that they will, both movies will start at the same time would be 8 p.m. Follow me? So remember, you select every prime factors that occurs, raised to the greatest power to which it occurs in this factorization. You have to pick all the primes, 2 and 3, okay? Okay, if you multiply these, you know, did you follow me how I got the LCM? You get 240 minutes, which is same as 4 hours. So if they started at 4 p.m., the next time that they start at the same time would be 4 hours later, which would be 8 p.m. Okay? All right, Brian, are you doing okay?
I'm with you.
Okay, all right. Okay. Let's go. All right, let's go to our PowerPoint again. All right. Oops. Now, here becomes easier. We talked about number theory. And other things are numbers are called integers. Remember, what were the natural numbers? Yeah, it goes all the way up. Okay. When we talk about integers, we can also include the negative numbers, but they must be whole. They cannot have a fraction. So you have 0, this is origin, 1, 2, 3, and -1, -2, and -3. These are called integers. So tell me, which one is bigger, integers or natural numbers?
Natural numbers.
No, integers, because natural numbers cannot have negatives. But in integers, you can have negatives. So actually, integers are twice the natural numbers. Because you see, natural numbers, you can only have 1, 2, 3. You cannot have -1, -2, -3. But integers can. Following me? Okay. So we will talk about addition, subtraction. When we add integers, if they are same sign, the same sign remains. If they have, you know, if they have opposite signs, the one that is bigger overrules, dominates. Same with the subtraction. In multiplication and division, if they are of the same sign, the answer is always positive. If they are of the opposite sign, the answer is negative. But I always say that in the Bible, you know, in the mathematics, you have minus times minus, you get positive. But in the Bible, negative times negative is not positive. Sin times sin doesn't give you something positive.
Right.
Okay. All right. Now as we do some example, this become more clear. Now, when we talk an integer, the set consists of natural numbers 0 and the negatives of the natural number is a set of integers. So we have 0, and positive integers, negative integers. Natural numbers is only has positive numbers, not the negative. So if you have a number line, this is called the number line. This is called the origin, and then you have 1, 2, 3, 4 positive, but you can also have -1, -2, -3, -4 negative. These are opposite of one another. All right? We use these symbols, this meaning less than and this meaning greater. If a number is here, means this number is less than whatever it's here. If the number is inside here, it means it's greater than the number that is outside. For example, now here the thing that you got to be careful when you talk about integers and positive and negative numbers. Look at -3 and 4. Which one is bigger?
-4.
No.
Um,
No, 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 no. -4. I mean, if you're talking, if you're saying by its absolute value, I agree. But when you look at the number line, 3 is here, -4 is here. The difference between these two numbers is it's 7 units. -4 is 7 units less than number 3. You go 1, 2, 3, 4, 5, 6, 7. Following me? Look at tell me how, not this one. Which one is bigger, which one is smaller? -1, -5. Which one is bigger, -1 or -5? That's right. The number closer to the origin, whatever you go this way to the right, is larger. -1 is greater than -5. Let me give you an example. Which one is the largest or oldest? 1st century BC or, how can I say that? Okay. Let me give you an example that makes sense. Okay. If we are talking about BC, 553 BC, as we are moving forward, does the number increase or decrease? No, no. Let's say you were at the time of Malachi, the last prophet, okay? And then we have the 400 years of silence, yes? Okay, so when it starts 400 years before Christ, I wait another 100 years. Now, what's the year now? No, no. If I was, for example, if I lived 100 years, which I don't think so, but I lived at the time of Malachi, approximately 400 years before Christ, okay? Because after Malachi, the 400 years of silence starts. Agree? Okay. Now I live 100 years. How many more years is left of that 400 years of silence? So I moved from 400 BC to 300 BC if I lived 100. So in the BC, just like the integers, 0 is the origin, birth of Christ, okay? As we move forward in BC, the years become less. Agree? So in the same way, if you have -1 and -5, here, look at the number line. -5 is here. -1 is here. What's the distance between -5 and 0? 1, 2, 3, 4, 5. What's the distance between -1 and 0? Just 1 unit. So this is bigger.
Use the BC year.
Oh, okay. If, for example, I mean, think of this is the timeline. Let's say I was here, okay, 400 years before birth of Christ, and let's here say this is the birth of Christ. Okay. Now, here are the years of silence, 400 years of silence, 1, 2, 3, and 4, okay? So I just think of each of them as a century. Now, if I'm here, and if I lived 100 years, I come here, all right? So I'm still in these years of silence, but only if I last 300 more years, then it will be over. But I still have 300 more years to go. All right? Brian, are you doing okay?
Yeah.
Okay, let's now talk about -5 and -2. Which one is bigger? -2. So if I want to write those symbols, I put -2 inside these things. So -2 goes inside and -5 would be outside. Following me? Tell me, 0 and -3, which one is bigger?
Brian, I need a shot.
0.
0, yeah. 0 is bigger than -3. The 0 is here, -3 is here. All right? Let's move on. Now, okay. If you're talking about absolute value, the thing that you just said, Brian, that's different. Absolute value only talks about the distance. For example, let's go back. The absolute value of -5, what's the absolute value of -5? 5. Yeah, I'm just talking about the distance between that number and 0. Doesn't matter, it's negative or positive. Actually, we don't talk about negative distance. We only have positive distance. So it could 1, 2, 3, 4, and 5. What's the absolute value of -3? At its absolute value.
3.
3, just 3. Okay. All right. It is,
Also, absolute value has nothing to do with
you're looking at its distance from 0.
also position.
Yes. Okay. Now, rules for addition of integers. Again, doing this is much easier than reading. If the integers have the same signs, just add their absolute value and put the sign, whether it's positive or negative. If they have different signs, then you have to subtract the smaller absolute value from the larger one and put the sign of the larger one. Now, sometimes when we add 2 digits, often we do regrouping. Let me do it. Let me show you an example that makes it much easier. Let's say we want to add -3 plus -2. Okay? They have the same sign. So, what's the absolute value of 3? -3, 3. What's the absolute value of -2? 2. Just add them together, 5, and put the sign. You get -5. In other words, -3 plus -2 means this. You are here, you're at the point -3. You want to go 2 more toward left. At least where I'm looking at. You go this way. So you come here to -5. Let me see, do I have an example? Okay, here, good. If I have -1 plus -8, here you're at -1. You want to add -8 to it. Again, they are the same sign. So you add the absolute value, you get 9, and you put the sign. But to visualize it, if you're here, -8 means you go that way. So 1, 2, 3, 4, 5, 6, 7, 8. We come to point -9. All right? Are you doing okay, Brian?
Yes.
All right. Now, about multiplication is much easier because always remember, if you have the same sign, you always get positive. If either of them, doesn't matter, smaller or bigger, it's of a different sign. If you have opposite sign, you always get negative. Plus times plus is plus. Minus times minus is plus. But if you have anything different, you get negative. And doesn't matter what is bigger, what is smaller. All right? Oops. Now, evaluating exponential expression, because exponent indicates repeated multiplication, rules for multiplying real numbers can be used to evaluate exponential expression. Let's look at page 244 of our textbook. And do some of the example here. Go to share screen. All right. For example, we have -6 to power of 2 or exponent 2. So if I want to solve this problem, -6 to power of 2, it means -6 times -6, correct? Negative times negative is positive. Remember, anytime you have the same sign, you always get positive. 6 times 6 is
36.
36. Okay. Now, let's do, there was one I wanted. You know, this is the same for all of them. Oh, this one is good. Number B, it says -6 to power of 2. Now, okay. You guys tell me how to do that. -6 to power of 2.
6 times 6.
Okay, 6 times 6 is equal to 36. What should be its sign?
Negative.
Negative.
Minus. Yeah.
Because this 2 is only for the 6. It's not for the negative. Remember, it's 6 to power of 2. Do you see the difference between these two? The first one is -6, the whole thing to power of 2. This one is -6, only the number 6 to power of 2. So, all right?
Yep.
And the rest are the same. Okay. Let me give you just one example of the addition when the numbers are different. For example, can you tell me if I add in +5 minus 12, what's the answer? You have different signs. +5 minus 12. If I have the number line, this is 0. Minus 12 would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 would be here. Forgive my drawing. 5 would be 1, 2, 3, 4, 5. 5 would be here. So 5 is here, minus 12 is here. When we are adding numbers, integers that have different sign like this, we are actually finding their difference. We're actually subtracting. So you have to subtract 5 from 12, which you get 7. And put the sign of the larger number, -7. If I have 5 plus and 12 negative, if I'm here and if you want, in other words, means you are here, go 12 points in the opposite direction. So I come 5 and then 7. 1, 2, 3, 4, 5, 6, 7. I'd be here. Okay? Are you following me?
Yes.
Okay, good. Are you okay, Dennis? Okay. So, Now let's go back to our PowerPoint. The division are the same as multiplication. If they have the same sign, always positive. If they have different signs, always negative, okay? So for multiplication and division is simple. If the same signs, positive. The opposite sign, mixed signs, negative. Addition and subtraction, if the signs are the same, just if you're adding, add the absolute value and put the sign. If you're subtracting, the same thing. But if it's a mix, like the example that we just saw, you're actually subtracting. And then put the sign of the larger number. All right? Now, order of operation is very important. Starts from within the group, from within the parentheses. Then do the exponent, do the multiplication and division, then do addition and subtraction from left to right. In order to remember this, we have this. Parentheses, exponent, multiply, divide, add, and subtract. And I have this. Please excuse my dear Aunt Sally. Please for parentheses. Excuse exponent. My dear, multiplication and division, and Sally, addition and subtraction. Okay, so let's look at, for example, let's go to page 246 and 247 of our textbook. Okay, let's. Okay. I'm at, page 246, 246, example 7. We have 6 to the power of 2 minus 24 divided by 2 to the power of 2 times 3 plus 1. Now, if you remember that rule, please excuse my Aunt Sally. We start with here and we say exponent. I take care of the exponent. 6 to the power of 2 is 36 minus 24 divided by 2 to the power of 2 is 4 times 3 plus 1, okay? So first I took care of the exponent, all right? Then I perform multiplication and division from left to right. So we get 36 minus 24 divided by 4. From left to right, I start my multiplication and division. 24 divided by 4 is 6. Okay, times 3 plus 1. Again, 36 minus, from left to right, do the multiplication. 6 times 3 is 18 plus 1. So 36 minus 18 is 18 plus 1, 19. Okay? If the mistake that many people do is when they come here, they think that, okay, they add 3 plus 1, 4. No, 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 no. First, take care of the exponent, then do the division or multiplication. And actually, the division takes priority. So 24 divided by 4, 6. Then I multiply. And then I add. Please forgive my Aunt Sally. All right. Now let's look at page 247. Page 247, example number 8. We have minus 6 to power of 2 minus 5, 7 to power of 2 times minus 3. Okay, so first we take care of we work from inside the parentheses. Minus 6 to power of 2. I first take care of here, inside these parentheses. 5 minus 7. Okay, these are two integers, different sign. This is plus, this is negative. What should I do? I subtract. 5 minus 7 is 2.
Is 2.
And negative 2, because
Negative
the
2.
bigger number is negative. Okay, times minus 3. Then I take care of the exponent. Minus 6 to power of 2 is minus 6 times minus 6 minus 2 to power of 2 is minus 2 times minus 2 times minus 3. Minus 6 times minus 6. Two integers multiplying the same sign. So the sign should be
Positive.
positive. 6 times 6, 36. Minus. Here, minus 2 times minus 2. You have, let's do it from here, from left to right. You have two integers multiplying by each other, and they have the same sign, so the sign should be positive. 3 times 2 is 6. And then here, oh, okay.
Wouldn't you go 2 times 2 is 4 times 3?
No, you see, 2 times 3 is 6. But clean up here.
Yeah, but you work right to left and not left to right.
Yeah, I go from this way. It doesn't matter. You can do it that way too. You still get the same. But let me clean up here. Okay. Minus 3 times minus 2 is plus 6. Plus 6 times minus 2 is, they have opposite numbers. So you get minus 12. Yes?
Yes.
So I have plus 36 minus minus 12. Now this minus multiplies by this one. This is like minus 1. So I get 36 plus 12. Are you following me? Brian, are you okay?
I'm trying to think of that rule.
Okay, let me do this part again.
So 2 positives are positive, 2 negatives are positive.
Okay, let's just do it again. We have minus 6 to power of 2 minus 5 minus 7 to power of 2 times minus 3. Okay? Remember, this here is plus minus 1. I can put number 1 here. It makes no difference. Just put this 1 here just to make it easier for you. Okay? I can have 1 or it doesn't matter. 1 times any number is that number itself. All right? So first I started from inside these parentheses. 5 minus 7 is subtraction. It's 5 minus 7 is 2 negative because the larger number is negative. So I have, this becomes minus 2. I no longer have the 6. And then I don't no longer have that subtraction. To power of 2 times minus 3. Okay, let's just think of this way, this part. Forget this part for a moment, okay? Minus 2 to power of 2 is minus 2 times minus 2. Then we have minus 3. All right, are you guys with me so far?
Yeah.
Okay. Minus 2 times minus 2, or you can go this way, it doesn't matter. Let's go this way, for example. Minus 2 times minus 2 is plus 4. Yes?
Yeah.
No, I have minus 3. Now, 4 times minus 3 is different sign, minus 12. Okay?
Yeah.
Now, remember, I had this minus 1 here from up here. So I put it here. So I have minus 1 times minus 12. What's the answer?
12.
Plus 12. So I got this part. Now, let's take care of this part. Minus 6 to the power of 3 is minus 6 times minus 6, which is, tell me, 36 positive. So I have 36 positive plus 12 positive. What's the answer?
48.
48 positive. Is that clear?
Yep.
Okay, all right, good. Okay, let's go back to our PowerPoint. All right. So parentheses, exponent, multiply, divide, add, and subtract. Multiply, divide, and subtract, and let me see. Yeah, from left to right. Remember, working from left to right. All right. Do multiplication for addition and subtraction, for multiplication and division from, again, left to right. All right? So we talked about, now, rational number. What's a rational number? The set of rational numbers is denoted by Q. Set of all numbers of the form P divided by Q, where P and Q are integers and Q is not 0. You cannot divide a number by 0. Now, every rational number, when it's expressed as a decimal number, that decimal number can be terminating or can be a repeating decimal number. Now, again, we will talk about this as we see. For example, fundamental laws of rational numbers. You know, if we have A divided by B, given a number C not equal to 0, if you multiply the numerator and the denominator of a fraction by a number, it makes no change in the value. Now, what I mean is this here. Look at this circle. This is half of it, yes? I can write it as 1 over 2, yes?
Mm-hmm.
If I multiply both top, the numerator and the denominator, by the same number, it makes no difference. You get 2 over 4. The only difference, the only change that I'm making, I'm saying instead of dividing this picture, this diagram, into 2 parts, I have divided it into 4 parts, and I have chosen 2 out of 4, which is the same as half. All right?
Mm-hmm.
Let's continue. Please, if there's anything not clear, anything you want me to go over, let me know, okay? Now, we can have positive mixed number. We can convert them to improper fraction. Multiply the denominator of the fraction in the fixed number by an integer preceding it. Add the product to the numerator. The denominator stays the same. Okay, let me show you what I mean. Let's go to page 252. Example on page 252. Let me go here. All right. So we are on page 252, example 2. It tells us convert 3/4 to an improper fraction. This is this number here, 3/4, is called a mixed number. Okay, this is called a mixed number. We want to convert it to an improper fraction. What you do is this. You take 5, multiply it by 3, add it to 4. So it would be 5, the denominator stays the same, 5 times 3 plus 4. So it would be 5 times 3 is what? 19. I mean 15. Plus 4 becomes 19. And the 5 is still the same. So the final answer is 19/5. This is called improper fraction because it can be simplified. 19 is greater than 5. And in fact, to do the reverse, to convert an improper fraction to a mixed number, you divide 19 by 5. 5 goes to 19 3 times, you get 5, 15, and the remainder 4. So this goes to the numerator, this goes to the denominator, and this becomes the integer here. This is called a mixed number. This is called improper fraction. Okay? So let's go back to our PowerPoint. Okay. For example, mixed number and improper fractions. A mixed number consists of the sum of an integer and a rational number expressed without the use of an addition sign. So think of these graphs. 2 solid yellow circle and a circle that has only 1/4 of it yellow. I write it 2 plus 1/4, but I don't write the plus sign anymore. Or if I want to write it as an improper fraction, take 4 multiplied by 2, 8 plus 1, 9. Okay? Which we just did is checkpoint 252. All right? This we just did that also at the same time. If you want to do the reverse converting, positive improper fraction to a mixed number, you just divide it. I just showed you. In other words, for example, you have, this is called an improper fraction, 7/4. If I want to convert it to a mixed number, I divide 7 by 4. 4 goes to 7 one time. The remainder is 3. 3 becomes the numerator. 4 becomes the denominator, and the quotient 1 becomes the whole number. And we did that, 252. Let me see on page 253. It's the same thing. Maybe just let's do one example. Example 4 on page 253. So if I'm on page 253, example 4, and I want to do number B. Okay, I have, where is it? Okay, I have 7/11. It says Write it as a decimal. So you want to divide 7 by 11, okay? Now 7 is smaller than 11, so you have to put 0 and a decimal point here, and then you can put a 0 here, all right? Then multiply this. 11 goes to 76 times, all right? I get 4. Now, if I can add another 0 here and continue the division, 11 goes to 43 times. I get 7. Now, tell me, if I continue, if I put 0 here and continue again, I get 66, 4. Again, put 4 here, and it continues. So this thing continues. All right? It's non-ending. All right. Any questions so far? Okay, good. Are you okay, Dennis? All right. Okay, let's go back to our PowerPoint. Are you guys doing okay? Do you need a break, or shall I continue?
And continue.
Okay, good. When we do multiplication of fraction again, if we have two fractions, just multiply the numerator and the denominator. 2 times 3 is 6, 5 times 4 is 20. You can simplify it. 6 can be simplified by 2, it becomes 3. 20 divided by 2 is 10. All right? Division. Division is just like that, exactly except for one thing. If I have 4/5 divided by 2/3 is the same as 4/5 times 3/2. So I just invert this one. I invert the divisor. Okay? And then I do the multiplication. 4 times 3, 12. 5 times 2, 10. And you get 12/10. This is called an improper fraction. So I change it into a mixed number. 10 goes to 12 one time, and then you will have, if you simplify it, it becomes 2/10, or you simplify 2 by 2 is 1, 10 by 2 is 5, so it would be 1/1/5. Do you follow me, or do I need to show it to you? How many times 10 goes to 12?
Once.
One time. Yes?
Yep.
Okay. Then I get 10 minus 12, remainder 2. So I will have 2 over here, and the denominator would be 10. Yes?
Mm-hmm.
Then I simplify. 2 divided by 2 is 1. 10 divided by 2 is 5. Okay? Can you follow? Or I can show it to you on the pad if you want. You guys doing okay?
Doing good.
Dennis, are you okay? Okay. No problem. Don't worry. When you want to add fractions, you have to find a common denominator, or the common multiple denominator, the lowest common denominator. To add or subtract fraction with common denominator, we add or subtract their numerator and keep their denominator. Again, let me, by an example, makes it much more easier. Let's say we want to add two fractions, 2 1/3 plus 3 1/4. 3/4, okay? And this is the visualization, right? So I have, first of all, just add these integers. 2 plus 3, 5. So the final answer will have a 5 right in front of it. Then you add 1/3 by 3/4. In order to do that, you must make their denominator the same. I want to change the denominator of this number to 4. How can I do that? multiply the top and the bottom, the numerator and the denominator, by 4. Remember, we said that in the beginning, if you multiply a fraction, the top and the bottom, by the same number, it makes no change in its value. Remember that? So I want to make their denominator the same, otherwise you cannot add them. So I multiply this, the top by 4 and the bottom by 4. I get 4 over 12. Okay, oops. 4 over 12, okay? Now I come to this one, multiply the top and the bottom by this denominator. 3 over 3, I get 9 over 12. Now I have their denominator the same. I have 4 over 12 plus 9 over 12. Are you guys following me?
Mm-hmm.
Okay. Okay. So you add these two, now you have the common, they have the same denominator, you just add their numerator. So you get 13 over 12. 4 plus 9, 13 over 12. Now this is improper fraction. I have to change it to a mixed number. So this is like 13 divided by 12. 12 goes to 13 one time. So I get the integer 1. The 12 comes here, and the remainder is 1. Okay? So I have 1, 1/12. And remember, we had 5 from here. We added these two. So 1 plus, I have 1 over 1/12 plus 5 is 6, 1/12. Okay? Fractions, when you want to work with a fraction, you have to make their denominator the same. In order to make the denominator the same, multiply the first fraction, both top and bottom, by the denominator of this one, the second one. Then multiply the second fraction, the top and the bottom, by the denominator of this one. Then you add them together, you get 13 over 12. And then this becomes an improper fractions. And you simplify this 1 over 1/12, and 1 over 1/12 plus 5 is 6, 1/12. All right?
Got it until when we get the test.
Okay. You're okay, Brian?
Yep.
All right, let's continue. We come to irrational number. One of the famous one is the pi, which I have an article. You can read that in the next lesson. Very interesting. Oops. Irrational number is a real number whose decimal representation is non-terminating and non-repeating. Like that, the one that we just did on example, page 253, that was not an irrational number because the number was repeating 6, 3, 6, 3, 6, 3. But you see, irrational number like pi, the number is not repeating. It's 3.141592, it continues. Now, every non-negative real number, A, has a unique non-negative square root. We are talking about the square root, principal square root, which is written like that, and this sign is called radical sign. In other words, for example, the square root of 4. Can you tell me what's the square root of 4? 2, exactly. So if I have irrational number 2 square root, this is the root. This is the number that we want to get the root of to the nth degree. Would be when the roots are the same, you just put the radical sign, put the n, and multiply. It's the root. Most for what we use is 2. We say square root, but it can be 3, it can be 4. Division, same thing. As long as the n is the same, you just put the radical n and divide a by b. All right? And b should be greater than 0. and A is not greater or equal to 0. B cannot be 0. Oops. Now let's look at some of our example on page 266, 267. For example, let's do 266 and 267 and 268. Let's go to our pad here. On page, so I'm on page 266, example 1. It tells us, let me see. Yeah, I guess that's good. The square root of 75. Well, here comes those factorization that we talked about helpful. 75 is 25 times 3. And 25 is 5 to the power of 2 times 3. Now, this 5 to the power of 2 comes out of the square root sign, becomes 5. 2 divided by the square root is 1, so it becomes 5, the square root of 3. All right? If I do another one, let's say on page 267, example 2, we have a square root of 2 times square root of 5. So remember, the n is the same, so I write square root of 2 times 5, which is equal to square root of 10. Okay? That's basically all you need to do. Or, I'm sorry? Yep, that's the end of it. Let me see anything else. Let's say example 3 of that page. We have a square root of 75 divided by square root of 3. Okay, that is equal to, now since the roots are the same, I can write one radical sign, 75 divided by 3, which is equal to 75 divided by 3 is 25. And the square root of 25 is?
5.
That's right. Let's see, anything else? Okay, let's do example 4 on page 268. We have 7 square root of 2 plus 5 square root of 2. Okay, these are the same, so you can factor it. So it will be 7 plus 5 square root of 2. Are you following me?
Mm-hmm.
And 7 plus 5 is 12, so square root of 2. That's the answer. Okay. Anything? Do you have any question in this part?
Unless, when we start doing that,
Yeah. You got to do practice. I encourage you to go over this example in your textbook and just practice. You're okay, Brian?
I am.
All right, let's go to our PowerPoint again. Now, if you look at this here, this diagram, you have real numbers. This whole thing, all the numbers that you have. The whole real numbers can be divided to two parts, rational and irrational. Irrational, just continue. It's never ending. The rational numbers are consist of these parts. Remember, first set we talked about the natural number, the counting number, 1, 2, 3, 4, 5, and so on. Then we talked about the whole number. You add 0, became the whole number. Then we talked about integer. We added the negative integers, okay? And then we talked about the rational number and not irrational number. These two form the real numbers.
Question, just a generic question. Does it mean for, I speak for myself, that math is like, well, does it mean that if I understand the information of how natural numbers work and relation to whole numbers, then I will be able to handle mathematical problems?
Yes, yes. But, you know, the math is like a language. In order to learn any language, you start with what? Alphabet. You learn the alphabet. Then you learn the words. Then you learn the grammar. Then you make sentences and read, translate, and all that. But all starts with alphabet. And what we are doing in this course here, just familiarizing ourselves with alphabet and some of the rules. Okay? This is important, some of the properties of real number. If an operation is performed on any or two elements of a set, and the result remains in that set is a closed set. Now, there are three important properties: commutative, associative, and distributive. What does it mean? It means simply, A plus B is the same as B plus A. It doesn't matter. 2 plus 3 is the same as 3 plus 2. Or A times B is the same as B times A. 2 times 3 is the same as 3 times 2. For any real number, A's and B's. Associative, for addition, if it doesn't matter whether I add A and A plus B, and then I add C, or I add first B and C, and then I add A. Same with multiplication, A times B times C. I can multiply A and B first and then multiply by C, or I can multiply B and C first and then multiply by A. Distributive means I can multiply A over an addition. A times B plus C is A same as A times B plus A times C. Okay? Oops. Exponent and scientific notation. When you have this kind of expression, 5 to the power of 2, 2 is referred to an exponent. And this, then when we have 5 to the power of 2 times, or let's say 2.4 times 10 to the power of 2, or 5 to the power of 2, that is called a scientific notation. We read 2 as 5 to the second power, or 5 squared. And the 2 is considered as an exponent. Now, let's go to page 282 and 283 of our textbook. And you have the properties of exponent there. Let me maybe some of them share some of them with you. Again, if I have b to the power of m multiply b to the power of n, you know, the b is the same, but m and n are different. The exponent is different. It's the same as b to the power of m plus n. example, 2 to power of 3 times 2 to power of 5 is the same as 2 to power of 3 plus 5, or 2 equal to power of 8.
And that will apply across the board.
Yeah, provided that we have the b the same, see, 2 and 2, and we have multiplication. Don't forget that.
Question, if they're different, how do you do that?
No, can't do that.
Oh, no, I mean, that's-
Then you just have to, if I have, for example, 2 to power of 3 times 5 to power of 2, I just have to multiply 2 times 2 times 2 times 5 times 5. Okay? Now here, another one, another rule. If I have b to power of m and then the whole thing to power of n is the same as b to power of m times n. If I have 2 to power of 3, then the whole thing to power of 4 is the same as 2 to power of 3 times 4, 12. Or if I have b to power of m divided by b to power of n, then the whole thing is equal to, again, remember, the b must be the same, b to power of m minus n. If I have 2 to power of 3 divided by 2 to power of 5 is the same as 2 to power of 3 minus 5, which is the same as 2 to power of minus 2. Now, you got to change that. If a number is to power of a negative, you can change it by reverse it. It's the same as 1 over 2 to power of plus 4. Okay. If I have a number, any number, to power of a negative, this is the same as that number 1 over that number to power, the same exponent to power of positive. One over 2 to power of plus 3. Okay? All right. Okay, so the general rule is this: b to power of minus m is the same as 1 over b to power of plus m. All right? Okay, shall I continue? Let's go again to our PowerPoint. So, any number to power of 0 is equal to 1. Just remember that. b to power of 0, any number is equal to 1. And we talked about this one too. Any number to power of negative is 1 over that number to power of positive. We talked about these right now. You know, a times a, when they have the same base, just add the exponent. A to power of n times the whole thing to power of n is m times n. And when you have a division, you subtract the exponent. All right? Now, scientific notation is this. When you have a number times 10 to power of n, and a is any number greater than equal to 1 and less than 10. Okay, this form of writing, they call it scientific notation. All right, let's give some example. Now, first let me read this to you and then we go to the example. To change a number to a scientific notation, in a scientific notation to a decimal notation, if the exponent is positive, move the decimal point in number to the right. I mean, it's better to go to the example. You can follow this. For example, if you look at page 285, example 3, I will do it on the pad, but let me first wanted to show you with the board. We have 2.6 times 10 to the power of 7. So in the book, they write 2.6 times to the power of 7, and then they move the decimal toward right because the exponent is positive. So you move to the right that many number that the exponent is. If the exponent is negative, you move toward the left. So let's just do this to make more sense. For example, here, I am on page 285, example 3, number 8. We have 2.6 times 10 to the power of 7, okay? The exponent is positive, yes? So I move toward right. I move this decimal point, this is decimal point right here, this way, 7 times. So if I have 2.6, it moves 1, then 2, 3, 4, 5, 6, 7. And for these places, I put 0. So that is the same as 26 million. This is the same as this. Now, example B of the same page, if I have 1.1 times 10 to the power of minus 4. The exponent is negative. This is a decimal point, okay? So when it's negative, I move the decimal point this way, okay? So I have 1.1, then I need to move it 4 times this way. So it moves 1, 2, 3, 4, put the decimal here, 0, and then the decimal is not there. And for these empty places, you put 0. So 1.1 times 10 to the power of minus 4 is equal to 0.123411. Actually, no, I'm sorry, I made one mistake here. It moves for, so this is extra because when it moves here, this is 1.234. So you have this 1 0 is extra. Okay, do you follow me? All right, Brian, are you okay?
Yes.
All right. So let's go back to our PowerPoint. Okay. Converting decimal notation to scientific notation. This is just the reverse of what we just did. So let me again go back to our if I have, so I'm on page 286, example 4, number A, I have 4,600,000, oops, 4,600,000, okay. I want to convert that to a scientific notation. In order to do that, I move the decimal. You see, I count the 0. 1, 2, 3, 4, 5, 6. I come to the first digit here that is less than 10. But I as far as I can go, I go to this direction. To left, okay? So I put the decimal point here, 4.6 times 10 to power of, you tell me what?
6.
6. Because we went 1, 2, 1, 2, 3, 4, 5, 6. Or, let's see, if we have this one, 0.000023, I want to write it as scientific notation. So I want to move this decimal point over here. So I want to have 2.3 times 10 to power of, okay, 1, 2, 3, 4, 5. Okay? 5. But what should I put here? Minus, because I moved this way. All right? This is what we were talking about when we were saying about move the decimal point in the original number to the right, to the left, until you obtain a number greater than or equal to 1. Count the number of places you have moved to the decimal point to obtain the number in step 1. The decimal point, if the decimal point was moved to the left, the exponent is positive. If the move to the right, you need to have the exponent in negative. Okay? Let's move on. Okay, 287, 286. Okay, some of the multiplication in computation with scientific notation on page 287 and to page 288. Let's look at that. We have an example of multiplication on page 287, example 6. We have 3.4 times 10 to power of 9 parentheses times 2 times 10 to power of minus 5. So this is multiplication. This is same as because you see we can write it this way, 3.4 times 2. I take these two, put them into one print. Remember the associative property doesn't matter. A times B times C times C times D, you can either multiply A by B or you can multiply A times D and do the other multiplication. So I times 3.4 times 2 parentheses 10 to power of 9 times 10 to power of minus 5. So what property did I use? Yeah, it said A, B, C, D. You can multiply them either this way, or you can multiply A by D and B by C. Makes no difference. Okay? So now I have 3.4 times 2 is what? 6.8 times these two, the base are the same. Remember the rule, b to power of m times b to power of n is same as b to power of m minus n. 9 minus 5. So it would be 6.8 times 10 to power of 9 plus 5, or plus 5, or 9 to power of 14. Here, now, wait a minute. Oh, no. These are multiplication, not addition. I'm sorry. B times minus n, this should be multiplication. 9 times minus 5. So it would be, let me see, let me clean up here. So we get 6.8 times 10 to the power of 9 plus minus 5. No, I was right. I'm sorry. I got confused. 6.8 times 10 to the power of 9 minus 5 is 10 to the power of 4. Okay, you guys followed me? Sorry, I mixed up here.
I'm lost.
You're lost? Okay, let's do this again. All right, we have 3.4 times 10 to the power of 9, okay? Multiplied by 2 times 10 to the power of minus 5, all right? I said, remember the rule, A times B, B, C times D. You can either do it that way, or A times C is the same as times B times D. These two are the same, okay? So I get 3.4, I can multiply this by this, all right, times 10 to the power of 9 times 10 to the power of minus 5. Are you with me, Brian?
Yeah.
Okay, so far okay?
Yep.
Okay, 3.4 times 2 is 6.8, okay? Multiply, now I have here 10 to the power of 9 times 10 to the power of minus 5, okay? So this is same as, the bases are the same, 10 to the power of 9 plus minus 5. The rule was this, remember, b to the power of m times b to the power of n is the same as b to the power of m plus n, okay? So 10 and 10, so I write 10 and just I added their exponent. 9 plus minus 5. Are you with me?
Yep.
Okay. So that becomes, what is 9 plus minus 5? Same as 9 minus 5. Yes? That's same as 10 to the power of 4. Are you with me?
Mm-hmm.
Okay, so this whole thing becomes 6.8 times 10 to the power of 4. Are you following me?
Sorta.
No, listen. Okay, we had 3.4 times 10 to the power of 9 and 2 times 10 to the power of minus 5. We said we just multiply these two together, 3.4 times 2, we get 6.8. All right?
Okay, there it is. That's what I was looking at.
Okay, then 10 to the power of 9 times 10 to the power of minus 5. All right?
I got you.
Okay, good. All right, so you're okay?
Yep.
All right, you're okay, Dennis? Okay, good. Let's continue.
So how do you know how to distinguish between the associative property?
Okay, just remember those rules that mentioned in the book, or we had it right here. Let me go to the PowerPoint. Go to the beginning. here. Remember? Oh, come on. Remember? This is commutative. A plus B is the same as B plus A. 2 plus 3 is the same as 3 plus 2. This is the one distributive property that we are working. Oh, actually, no. We, that was, well, it's a form of distributive. If we have A, B, and C, and they are all being multiplied, or A, B, C, and D, it makes no difference. If you multiply A and B together, and B and C together, or if you multiply A times C first and B and E, or B and D next, because they are all multiplication. I'm just changing their place to make it easier for myself. I'm just moving one place from another. Okay. Okay, so we talked about these. We did that. Arithmetic and geometric sequences, a sequence in which each term after the first term differs from the preceding term, is called the arithmetic sequence. The amount by which each pair of successive terms differs is a common difference. Page 294. Let me check something here. Just one moment. Actually, yeah, that was this is the last one. Okay, so let me go to share screen. Okay, on page 294, let's go to page 294 and talks about the arithmetic and the common difference. For example, if we have, you see, we have 29, 31, 33, 35, 37. The difference between 29 and 31 is what?
2.
2. From 31 to 33, 2. From here, 2, 2. So the common difference for CD is 2. Writing the terms of arithmetic sequence, for example, write the first 6 terms of arithmetic sequence with the first term 6 and common difference 4. It tells me the first term should be 6. Okay, I'm on page 294, example 1. Okay, tells me your first term is 6 and the common difference is 4. So what should be the next number?
10.
10. And the next number?
14.
14 and 18, and it continues. 22 and so on. It tells me, let's do example number 2. Example 2, page 294. Tells me, write the first 6 terms of arithmetic sequence with A1B, the first term be 5, and the difference be -2. So the first term is 5. What should be the second term?
3.
3. What should be the next term?
1.
1. The fourth term?
It is 1.
-1. You go 1 to 0 and 0 to -1. What should be the next one? -3. The difference between -1 and -3 is -2. You keep going down by 2 units. Okay? Are you following me?
Yep.
So in general, if A1 is the first term, the second term is A1 plus D. And it continue. The third term would be A1 plus 2D, and so on. If the first one, A1, is, for example, here in our case was 5, D is minus 2, so the second term is 5 minus 2, 3, then 1, then minus 1, then minus 3, and go on, and so on. All right? Are you guys okay? All right.
Because brain freeze.
Okay. Sorry. Brian, are you doing okay?
I'm good.
Okay. Any question you have from homework assignment? Don't worry about so much about those 6 little known facts. Do your best. That's an open book, open internet. You can use internet, computer. You can talk to each other if you want. That's just like a research. And I will give you the answer later on. All right? So don't worry about it too much. You guys are doing okay. Just if you read the textbook and make sure you understand the principle. And if you don't, please call me. And if you need to talk to me, meet with me, I can, for those of you who are in San Diego area, you know, I can see you guys on Wednesdays at 11 a.m. I'm in admin building, room 317. Okay, but send me an email or a call me so I make sure to be there. I'm usually there during this time, but just in case. But I'm here to help you. Please don't hesitate to ask for help. All right. And again, for some of you, if you're late in submitting some of your homework, don't give up. I will still give you grade if you submit it. Okay? All right, everybody okay? All right. Okay, that's for tonight. Let's have a prayer and finish our time. Father God, I thank you for the opportunity to spend this time with my brothers and ask your blessing upon all of them, all the dear students, everyone, the brothers and sisters everywhere, and bless them and help them to understand these principles. Sometimes it may look so abstract and too much, but help them to be able to set aside each of them in their mind and see their relationship and see the pattern so that the understanding will become much easier. Bless all these dear students for your glory, the Lord Jesus Christ. For in your name we pray. Amen.
Amen.
You're dismissed.
Thank
Take
you.
care. Okay. Goodbye.
Bye.
Bye, Brian.
Bye-bye.
Goodbye.